Yes, the video have just split. It's 9 p.m. evening. Let's just continue.
Other instructions for manipulating the stack include push /pop for storing and retrieving the flags register. The pusher /papa instructions will store and retrieve the entire integer register state towned from the stack. Values for a simmed load or store are assumed to be packed in adjacent positions for the simmed register and will align them in sequential little-endian order. Some SSE load and store instructions require 16-bit alignment to function properly. The simmed instruction sets also include prefetch instructions which perform the load but do not target any register, used for cache loading. The SSE instruction sets also include non-temporal store instructions which will perform stores straight to memory without performing a cache allocate if the destination is not already cached, otherwise it will behave like a regular store. Most generic integer and floating point, but no simmed, instructions can use one parameter as a complex address as the second source parameter. Integer instructions can also accept one memory parameter as a destination operand. Program flow. The X86 assembly has an unconditional jump operation, Jmp, which can take an immediate address, register or an indirect address as a parameter. Note that most RISC processors only support a link register or short immediate displacement for jumping. Also supported are several conditional jumps, including JZ, jump on 0, JNZ, jump on non-zero, JG, jump on greater than, signed, JL, jump on less than, signed, JA, jump on above / greater than, unsigned, JB, jump on below / less than, unsigned. These conditional operations are based on the state of specific bits in the flags register. Many arithmetic and logic operations set, clear or complement these flags depending on their result. The comparison CMP, compare, and test instructions set the flags as if they had performed a subtraction or a bitwise AND operation, respectively, without altering the values of the operands. There are also instructions such as CLC, clear carry flag, and CMC, complement carry flag, which work on the flags directly. Floating point comparisons are performed via FCM or FICM instructions which eventually have to be converted to integer flags. Each jump operation has 3 different forms, depending on the size of the operand. A short jump uses an 8-bit signed operand, which is a relative offset from the current instruction. A near jump is similar to a short jump but uses a 16-bit signed operand, in real or protected mode, or a 32-bit signed operand, in 32-bit protected mode only. A far jump is one that uses the full segment base offset value as an absolute address. There are also indirect and indexed forms of each of these. In addition to the simple jump operations, there are the call a subroutine, and return from subroutine, instructions. Before transferring control to the subroutine, call pushes the segment offset address of the instruction following the call onto the stack. Ret pops this value off the stack, and jumps to it, effectively returning the flow of control to that part of the program. In the case of a far call, the segment base is pushed following the offset. Far ret pops the offset and then the segment base to return. There are also 2 similar instructions, int, interrupt, which saves the current, flags register value on the stack, then performs a far call, except that instead of an address, it uses an interrupt vector, an index into a table of interrupt handler addresses. Typically, the interrupt handler saves all other CPU registers it uses, unless they are used to return the result of an operation to the calling program, in software called interrupts. The matching return from interrupt instruction is IRET, which restores the flags after returning. Soft interrupts of the type described above are used by some operating systems for system calls. and can also be used in debugging hard interrupt handlers. Hard interrupts are triggered by external hardware events, and must preserve all register values as the state of the currently executing program is unknown. In protected mode, interrupts may be set up by the OS to trigger a task switch, which will automatically save all registers of the active task. Examples: Hello World, program for DOS in MASM style assembly. Using interrupt 21H for output. Other samples use libx printf to print to stout. 21. Model small. Stack 100H. Data. MSGDB Hello World, $. Code. Start. Move 09H, display the message. LeadDX, MSG. Int 21H. MoveX, 4C00H, terminate the executable. Int 21H. End start. Hello World, program for Windows in MASM style assembly. Requires /coff switch on 6.15 and earlier versions. 386. Model small c. Stack 1000H. Data. MSGDB Hello World, 0. Code. Include elablib.lib. Include elablibcruntime.lib. Include elablibicat.lib. Include elablegacy_steel_definitions.lib. Extern printf near. Extern exit near. Public main. Main proc. Push offset MSG. Call printf. Push 0. Call exit. Main emp. End. Hello World, program for Windows in MASM style assembly. Image base equals 0x00400000. Percent define RVA, x, x0x00400000. Section.text. Pushed word hello. Called word, printf. Push byte +0. Called word, exit. Red. Section.data. Hello DB Hello World. Section.idata. DDRVA, MSVCRT_lookuptable. DD-1. DD0. DDRVA, MSVCRT_string. DDRVA, MSVCRT_imports. Times 5 DD0, ends the descriptor table. MSVCRT_string DD MSVCRT.dll, 0. MSVCRT_lookuptable. DDRVA, MSVCRT_printf. DDRVA, MSVCRT_exit. DD0. MSVCRT_imports. Printf DDRVA, MSVCRT_printf. Exit DDRVA, MSVCRT_exit. DD0. MSVCRT_printf. DW1. DWprintf, 0. MSVCRT_exit. DW2. DWexit, 0. DD0. Hello World, program for Linux in MASM style assembly. This program runs in 32-bit protected mode. Build, NASM FLF staps name.asm. Link, LDO name.o. In 64-bit long mode you can use 64-bit registers, for example RAX instead of EX, RBX instead of EBX, etc. Also change FLF for FLF64 in build command. Section.data, section for initialized data. str, db hello world, 0 message string with new line char at the end, 10 decimal. str_n, $, str, calcs length of string, bytes, by subtracting the str's start address. From this address, $symbol. Section.text, this is the code section. Global _start, _start is the entry point and needs global scope to be seen by the linker equivalent to main, in C/C++. _start, definition of _start procedure begins here. Move X, 4, specify the system_write function code, from OS vector table. Move X, 1, specify file descriptor stout in new /Linux, everything's treated as a file. Even hardware devices. Move X, str, move start_address_ of string message to X register. Move X, str_len, move length of message, in bytes. Int ATH, interrupt kernel to perform the system call we just set up.
Yes, but I'm not a computer grammar, but I like to read this because then I better understand what programming code looks like. I've not looked at this before, that's the first time I do this.
In new /Linux services are requested through the kernel. Move X, 1, specify system_exit function code, from OS vector table. Move X, 0, specify return code for OS, 0 tells OS everything went fine. Int ATH, interrupt kernel to perform system call, to exit. Hello world, program for Linux in NASM style assembly using the standard library. This program runs in 32-bit protected mode. GCC links the standard C library by default. Build, NASM FLF staps name.asm. Link, GCCO name.o. In 64-bit long mode you can use 64-bit registers, for example racks instead of X, RBX instead of EBX, etc. Also change FLF for FLF64 in build command. Global main must be defined as it being compiled against the C standard library. Extern printf declares use of external symbol as printf is declared in a different object module. Linker resolves this symbol later. Segment.data, section for initialized data. String db hello world, 0r, 0h, message string with new line char, 10 decimal, and the null terminator. String now refers to the starting address at which hello world is stored. Segment.text. Main. Push string. Push the address of first character of string onto stack. This will be argument to printf. Call printf. Calls printf. Add ESP, 4, advances stack pointer by 4 flushing out the pushed string argument. Return. Hello world, program for 64-bit mode Linux in NASM style assembly. Build, NASM FLF64F dwarf hello.asm. Link, LDO hello.o. Default REL, use RIP relative addressing modes by default, so, foo, equals, real foo. Section.redata, read-only data can go in the .redata section on new /Linux, like .data on Windows. Hello, db hello world, 10 equals \n. len_hello, $, hello, get NASM to calculate the length as an assemble time constant. Write, takes a length so a 0 terminated C-style string isn't needed. It would be 4 puts. Section.text. Global _start. Move X, 1, __n_write syscall number from Linux asm/unist_64.h, x86_64. Move ed, 1, int fd equals stout_file no. Leah C, real hello, x86-64 uses rip relatively to put static addresses into regs. Move rdx, len_hello, size_t count equals len_hello. Syscall, write, 1, hello, len_hello, call into the kernel to actually do the system call. Return value in racks. RCX and R11 are also overwritten by syscall. Move x, 60, __n_exit call number, x86_64. XOR ed, status equals 0, exit normally. Syscall_exit, 0. Running it under stress verifies that no extra system calls are made in the process. The printf version would make many more system calls to initialize libc and do dynamic linking. But this is a static executable because we linked using LD without Pi or any shared libraries. The only instructions that run in user space are the ones you provide $strace._hello and gt/dev/null hash without a redirect. Your program's stout is mixed strace slogging on step, which is normally fine. exec._hello. ./hello 0x7FFC8B0B3570 /*51vars */ = 0. Write 1 hello world \n 13 equals 13. Exit 0 equals plus and exited with 0 plus and plus. Using the flags register. Flags are heavily used for comparisons in the X86 architecture. When a comparison is made between two data, the CPU sets the relevant flag or flags. Following this, conditional jump instructions can be used to check the flags and branch to code that should run. For example, cmp x jne do_something. Do_something. Do something here. Flags are also used in the X86 architecture to turn on and off certain features or execution modes. For example, to disable all maskable interrupts, you can use the instruction CLI. The flags register can also be directly accessed. The low 8 bits of the flag register can be loaded into R using the laugh instruction. The entire flags register can also be moved on and off the stack using the instructions push, pop, int, including into, and iRead. Using the instruction pointer register. The instruction pointer is called IP in 16-bit mode, IP in 32-bit mode, and RIP in 64-bit mode. The instruction pointer register points to the memory address which the processor will next attempt to execute. It cannot be directly accessed in 16-bit or 32-bit mode, but a sequence like the following can be written to put the address of next_line into X, call next_line. Next_line. Pop X. This sequence of instructions generates position-independent code because call takes an instruction pointer relative immediate operand describing the offset in bytes of the target instruction from the next instruction, in this case 0. Writing to the instruction pointer is simple. A Jmp instruction sets the instruction pointer to the target address, so, for example, a sequence like the following will put the contents of X into IP, Jmp X. In 64-bit mode, instructions can reference data relative to the instruction pointer. so there is less need to copy the value of the instruction pointer to another register. See also. Assembly